Hello, welcome to the new video. I hope you guys are doing good. So on this video we are going to talk about very important part of the applied statistics we call ANOVA. Okay, so we will discuss about ANOVA. What is ANOVA and how do we perform ANOVA? In the long form, it is called analysis of variance. Hypothesis testing concerning the means of three or more populations. Um, uh, we use F-test and the techniques is called analysis of variance. Do you remember if you have a two population, right? We use T-test, right? T-test, and there are several cases for the two population. But if you are comparing more than two populations, then we use F-test. Okay, this is the test we use, F-test, and the technique of using this is called analysis of variance. Okay, in short, it is called ANOVA. The T-test is designed to compare two populations. While comparing two populations with alpha equals to 0.05, there is 95% chance that we correctly conclude not to reject H0 when two populations means are equal. So what is it saying is, when you say alpha equals to 0.05, that is type 1 error, right? So with what that means is there is 95% chance that you correctly decide your conclusion is correct, meaning conclude not to reject H0 when they are when the two means are equal, right? But if you are comparing more than two, say three population for example, there will be three pair of such sample, population 1 and 2, 2 and 3, 3 and 1, right? So the probability of not rejecting H0 when it is true will be 0.95 times to the 3, which is almost 86%. Thus the probability of type 1 error, that is incorrectly rejecting H0 for the case of 3 sample using pairwise comparison, is 14%. In this case the type 1 error will be 14%. In 2 sample it was 5%, but if you use the same technique, so it will be 14% if you do the pairwise comparison. Okay, thus the comparison of means with pairwise t-test will result higher chance of rejecting the null hypothesis. Hence the previous method for comparison is not a good idea for more than or equal to 3 sample. Okay, in summary, as the number of sample increases, there is more chance that one of the sample have mean different from other samples, even if the sample are taken from the same population. And if there are k samples with c possible pairwise combinations, the type 1 error on doing the pairwise t-test is 1 minus alpha to the c. That will be the type 1 error if you do the pairwise comparison. Okay, where c is k times k plus 1. This is the number of combinations. That is the possible pairwise combination. That's what the c. Okay, c is the number of combination, which is k times k minus 1. For example, if you have 3 samples, right? If you have 3 samples, then what will be the c? What are the possible number of combination? That will be 3 times 3 minus 1 over 2, right? That will be how much? 3. So you see that this is one pairwise comparison, that is another pairwise comparison, and that is another pairwise comparison. So if there are 3 samples, there will be 3 pairwise comparison. That will increase the type 1 error is 1 minus alpha to the 3. So if alpha is 0.05, then 1 minus alpha will be 0.95 to the 3, and then subtract from 1. That will be the type 1 error. Okay, that will be the type 1 error, so which we will get about 14%. All right, let's next go to the next slide. What are the assumptions of the ANOVA? Actually, ANOVA is a parametric test. Okay, do you remember doing the parametric test, comparing the mean of the 2 samples, comparing the mean of 1 sample, z-test, t-test? All those are the parametric test. And also so in the parametric test we assume that the population is normally distributed, right? So similar to those problems, In the ANOVA also we have some assumptions. The number one assumption is the population from which the sample are obtained must be normally distributed or approximately normally distributed. If they are slightly deviated from the normal distribution, you are okay to use. But if it is very much deviated then from the normal distribution, then you should not use the this ANOVA test. Okay, we'll decide at the end of the ANOVA, one-way ANOVA. I will tell you. I'll discuss some of the points, like in which situation we use ANOVA, which situation we don't use ANOVA, those kind of things. The next assumption is the sample must be independent of one another, meaning that it is not like a pairwise sample, like a dependent, the same subjects taken at different times. It's not like that. They should be all independent to one another. The variances of the population must be equal. This is important, okay? If the variances of the population are not equal or very much unequal, then we use different method, okay? But if the population variance are equal or almost equal, then we use the ANOVA. So that's the thing that we use. Basically, when you do the ANOVA in R, this is the thing you test, this one and this one for the assumption. You test whether the population are normal distributed or not, and another thing you test is whether population variances are equal or not. Okay, these are the two assumptions you test. The sample must be a simple random samples, one from each of the population, meaning whenever you collect the sample, they must be a random sample, simple random samples you collect from the population. So those are the four assumptions you need to have, you need to satisfy to use ANOVA. Single factor ANOVA. What do you mean by single factor ANOVA? We also call one-way ANOVA for the single factor ANOVA. Okay, we also call one-way ANOVA. Okay, we also call one-way ANOVA or single factor ANOVA. What does that mean? If the comparison is made for a single factor, we call single factor ANOVA. For example, comparing grades with number of absences, comparing weight gains with specific diets. So you are comparing the means with only one category, under only one category, or you say only one factor. Okay, then that is the one-way ANOVA. So what are the steps to perform one-way ANOVA? Number one is write H0 and H1. What is H0? H0 is mu1 equals mu2 equals mu3 equals, meaning all the population have the equal mean. That is H0. And H1 is not all means are equal. What does that mean? It doesn't mean that all of them, mu1 is not equal to mu2, mu2 is not equal to mu3, mu3 is not equal to mu4. It doesn't mean that way. What does that mean is at least one of these mean is different from the other means, right? So at least one. That means at least one of the mu1 or mu2 or mu3 or mu4, right? Mu is or you say r, right? R different from other. Okay, that's what the alternative hypothesis is. And to find out, the step 2 is find the test statistic or test value. This is the formula we use. We use SB square, meaning the variance of the between groups. SB is the between groups. Variance of the between groups divided by variance of the within groups. So between groups variance divided by the within group variance. So what does that mean? How do we find out the between group and within groups? That's what we discuss here. Okay, where S square B is the variance between groups, called group mean square. That's what we call group mean square. Okay, and it's given by this formula. What is that? N1 and X1 bar is the mean of the first sample minus X bar GM, meaning the mean of the whole population. Okay, mean of all data, the whole samples. Okay, not the whole population but whole samples. So N1 is the size of the first sample, X1 bar is the sample mean of the first sample, minus XGM bar is the mean of the whole sample, overall samples, and then square of that, plus N2 similarly, size of the sample 2, mean of the sample 2 minus the general sample mean square, plus, and then do all those things for each of the sample, divide by k minus 1. What is k? K is the number of samples, right, or number of groups, I would say. So k is the number of samples or group. I have written it here, okay, that is k. And s squared w is the variance within groups, also called mean squared error. This is group mean squared, this is mean squared error, okay. So MSE, and is given by s squared w equals to n1 minus 1 s1 squared plus n2 minus 1 s2 squared plus, and continue that way, divide by n1 minus 1 n2 minus. It is, do you remember, it is similar to the weighted arithmetic mean. Weighted mean, in the weighted mean, what you used to do is find the mean of the first sample times sample size, mean of the sample times sample size, and so on, and divide by the size of the samples. It is similar to that, but here it is weighted mean of the sample variances, where the weights are the degrees of freedom or the sample size minus 1 in each of the sample, right? That's how this is. So once you find out s squared b and s squared w by using this formula, then you find out the test value given by s squared b divided by the s squared w. Step 3 is finding the critical value or the p-value. How do I find the critical value? To find out the critical value or p-value, we always use the right tail test. Don't forget that. We have so many other tests that we use just the right tail test, right? Right tail chi-square test. Do you remember that? Chi-square goodness of fit test, and we had homogeneity of the proportion. All those tests used right tail, right? But here we use right tail F test. Okay, there is a F table available. I will show you that. We use that F table, and the degrees of freedom is given by, because F table will have degrees of freedom on the left and then right. Okay, degrees of freedom of numerator and degrees of freedom of denominator. We'll have that. So how do I find the degrees of freedom of numerator? Is k minus 1, number of group minus 1, and degrees of freedom of denominator is n minus k. What is n though? N is the total data, number of total data, and then minus number of groups. That's how we find out the degrees of freedom of the denominator, where n is the total number of data. To find the critical value, we use F table with alpha and degrees of freedom of numerator and denominator. Again, we use right tail test, okay, right tail and denominator. We denote it by F, alpha, n1, n2. n1 is the degrees of freedom of numerator, n2 is the degrees of freedom of denominator, and alpha is the type 1 error, right, the alpha value. The region right to the critical value is called the critical region, okay. The region right to the critical value is the critical region because it is the right tail test. To find out the p-value, you can use the calculator FCDF, okay, and test value, and then 10 to the 10 is the big right value you take, and then n1, n2 degrees of freedom of numerator, degrees of freedom of denominator in the calculator. And decision is if the test value fall in the critical region, or if p-value is less than alpha, we reject the null hypothesis. Otherwise, we do not reject the null hypothesis. Okay, guys. By the way, I forgot to mention you, how do I find out the critical value? This is the p-value, right? This is finding the p-value. You can use PF in R, okay? You can use PF in R. You can do, but here for the p-value, you can use PF. For the critical value, you can use QF, okay? So what you need to do is you need to do QF and then 1 minus alpha, okay, because R always use the left area, okay. That's why since this is the right tail test, you need to do 1 minus alpha and then n1 and then n2. If you do that, you can find out the critical value, okay, in R. So that is F alpha n1 n2. That is basically, this is equals to QF 1 minus alpha n1 n2. That's what you use, okay, guys. And then to find out the p-value, and similarly, if you want to use R to find out the p-value, what you do is because it is the right area, right? So you do area right of the test value, right? So what do? You do 1 minus PF, right? PF, and then you do the test value, and then N1 and then N2. That's what you do to find out the P value using R. Okay, so this is the P value. I will show you in the R as well in one example. Okay, and the last, the decision is we discussed that already. Let's see one example. 19 pigs are assigned at random among 4 experimental groups. Each group is fed with different diet. The data with pig body weight after being raised in these diets are presented below. Diet 1, these are the weight of the pigs. Diet 2, diet 3, and diet 4. So, do the sample size equal? No, right? Because see, there are 1, 2, 3, 4, 5. Here you have 1, 2, 3, 4, right? Here you have 1, 2, 3, 4, 5. So some of the sample is 5, some of the samples are 4. We want to test whether 4 different feeds or the diets result in different body weight in pigs with alpha equals to 0.05. So basically we are comparing the average or the mean of the 4 samples, right? Mean body weight of the 4 samples. Note, here the body weight is depending on only one factor, that is feed, right? So that's what we call one factor. So the body weight is depending on only one factor. We are assuming that it depending on only one factor feed, a single factor. Each type of the feed is called the level or the factor. These are called the level or the factor. Thus this problem has one factor and 4 levels. Okay, there are one factor and the levels are, there are 4 different groups or 4 different categories, I would say. We follow the 4 steps to perform the analysis of the variance. So here H0 is all the mean are equal, H1 is mean are not equal, at least one of them. The general mean for the all data XGM, meaning how do I do that? You add all those and divide by 19, right? So that's what you will get, that is the X bar GM. Similarly, you find out the X bar of the first sample, second sample, third sample, fourth sample. So that is, these are the sample size of the samples. Feed 1, feed 2, feed 3, feed 4, so diet 1, diet 2, like that. And XI bar are the sample of each of, sample mean of each of the samples and the sample variance of each of those samples. That's what we found. We use calculator to find out those, or you can use R to find out that, not a problem. Okay. Now what is SB square? We found SB square is 111.47. Well, how do I find out SB square? Then SB square is found by using this formula. This is the variance between the groups. Okay, and then SW square is variance between the within the group. So that's the formula we use for that. So and then I found F is the F value or the test statistic or test value, SB square over SW square, which is 11.957. This is the test value. And the next step is find the critical value. We need to use the right tail test, F table. Okay, so what is alpha? This table is for alpha equals to 0.05. Okay, for different values of alpha you get different table, but this is for 0.05 and our question is asking for 0.05. so this is the table we need. Okay guys, now what is the degrees of freedom? How do I find out the degrees of freedom of the numerator? Degrees of freedom of the numerator is k minus 1, that is the number of groups minus 1, right? So that is 4 minus 1 is 3. I think I have done it here. Yes. The degrees of freedom of the numerator is k minus 1, that is 3. Degrees of freedom of the denominator is n minus k. N is, how much is n? N is 19. And then k is number of groups, right? That is 4. So 19 minus 4 is 15. So the degrees of numerator is 3, degrees of denominator is 15, and n is the total number of data. So thus the critical value is F alpha is 0.05, that's this table, and 3, 5. Degrees of numerator, degrees of freedom of numerator is 3, and then 15 is the degrees of freedom of the denominator. That's what you get. This value is the critical value. You see that? This is where we got the critical value. 3.2874. This is how you find using the table. But if you have to use the R, do you remember what code we did? We did QF to find out the critical value. We did QF and then 1 minus alpha and then N1 and then N2, right? So what is 1 minus alpha? QF, 1 minus alpha is 0.95. You see that? And then N1 is 3 and then N2 is 15. If you do that in your calculator, in your R, you will get, let me check. You will get, do you see that? Critical value is QF equals to, let me erase these things there, clear the console. Now let me run that. If I run this, then you will get the critical value is 3.287382. That's what you get. Okay. So using the p-value method, this is the critical value. And if you want to use the p-value, what you need to do is you need to find out the right area from the area right of the test value, right? Area right of this. You need to find the area right of this. So how do I find out the area right of this? This is the calculator you use, FCDF, and area right of this is 11.957, 10 to the 10, right area, right? And then the degrees of freedom of the numerator and degrees of freedom of the denominator. That's what you do. And that's what you get. But if you want to use R, do you remember how do we do using R? We did 1 minus PF and then 11.975 and then 3 and then 15. If you do that, R must give you the same value. Let us try if it gives different value, okay? So here we have p-value is 1 minus PF, 11.957 and 315. If I run this and find out the p-value, that's what you get, 0.0002933, right? That's what you got, 0.30 and then 29. So there are different F tables for different values of alpha. That's what I mentioned that already. So here, how do I decide? What is your conclusion? Since the test statistic F falls in the critical region, right? Because what is the critical value? Critical value is 3.2874. Anything right of this is the rejection region, right? Anything right of this is the rejection region. But what we got for the test value is 11.975. So it falls in the shaded region, right? Basically what is happening there is you have a F distribution. This is so 3.3 almost, right? And your test value is somewhere here 11.9, right? So since it falls in the critical region, so we reject. That's one way. Another way is, since the p is less than alpha, what is your p? P is 0.00029, right? So alpha is 0.05. Then we reject the null hypothesis. So what is the conclusion? There are not enough evidence that these four different diets have same effects in the peak weight gain. So we cannot say that all the means are equal. Let us complete this note. Let us read this note. If there are only two samples, k equals to 2, you can use t-test or ANOVA. So if you use ANOVA, this is fine, or you can use t-test, okay? Both will produce the exactly same result. But if you are testing the difference between the mean as a constant number other than 0, then t-test is applicable instead of the variance. Sometimes do you remember that we have, one time we have like, we were testing mu1 minus mu2 equals to 4 or 5. Do you remember the example that has like the average age of the men for gray hair to start graying hair is 30, and for women it was 34, right? And we wanted to test whether that difference of the age is greater than 5 or less than 5, like that. So in that case, if the right hand side is not 0, then the ANOVA is not useful. You will have to use the t-test, okay? But ANOVA is mainly for more than 2 samples, and then testing whether they are equal or not. That's when we use ANOVA. So while selecting groups, if they are not selected randomly, it is called fixed effect. Okay, fixed effect model or model 1 ANOVA. For example, in above problem, the 4 diet type are particularly picked to be tested instead of picking 4 random diets from all diet list. In case of the random effect model, the null hypothesis would be the peaks that have no effect in their weight. All other steps on the conclusion are the same. So this is the fixed effect because you have just 4 types of die, and then you are testing whether all the 4 types or the effect of these 4 types of diet have equal effects in the weight gain or not. But sometimes you have like 20 diets and you pick randomly 4 diets and then assign to the random group of picks. In that case, we call random effect ANOVA. Okay, that's what it is talking about. Okay, so there is another example. This is exactly similar to what we did. So a laboratory employs a technique for determining the phosphorus content of hay. The question arises, do phosphorus determination differ among the technicians performing the analysis? So to answer the question, each of 4 randomly selected technicians was given 5 samples from the same batch of hay. The results were given below. These are the phosphorus content on 5 samples of hay, and then these are technicians. They are giving those numbers. Okay, with alpha equals to 0.05, test whether the determinations of the phosphorus content are different among technicians. So here 80 is determination of the, so these are the very standard part, right? And I found the x bar gm, meaning the mean of all those. Look at this, all of these samples there are like the sample size are equal in each of those technicians, right? And then the sample size is 5 xi bar. We find out the sample mean of each sample, and then sample variance of each sample. We find out SB square. So between group variance is 3 and within group variance is 1.250. So the test statistic, we use the formula that we found 2.4. And then we find out the degrees of freedom of the numerator and degrees of freedom of the denominator using those formula 3 and 16. And then the with alpha equals 0.05, the test value, or sorry, the critical value is 3 and 16, right? So 3 and 16, 3.24. You see that? This is 3.24 there. So we got 3.24 as the critical value. Similarly, we find out the p-value is 0.1058, right? Since the test statistic f does not fall in the critical region, because what is the critical region? Because our critical value is 3.24, right? So you see that it is 3.24 somewhere here, but your test value is somewhere here, right? So this is the rejection region, right? But your test value falls here, so we do not reject the null hypothesis. Or p-value is greater than alpha, so we do not reject the null hypothesis. So we can say that there are enough evidence, or there are evidence that determination of the phosphorus content do not differ among the technician, meaning all the means are basically the equal. Okay, so in the next video we will talk about if the variance between the variance of these populations are not equal, how do I do the ANOVA? But this is it for the one-way ANOVA. Okay guys, thank you very much.